All right, well, we are at 3, so I'll go ahead and start talking logistics for the exam. So we are a week out right now. The exam is over chapters 1 through 4. You can bring a cheat sheet with whatever you want on the front of it, 8.5 by 11 sheet of paper. Anything you want to put on it is fine. The equation sheet that is on the practice question packet will also be provided during the exam. Actually, the first 2 pages of that packet will look pretty much like the first 2 pages of the exam. Exams are usually anywhere from 10 to 14 questions, and it splits about 1/3 multiple choice conceptual type questions and 2/3 calculation. That may be either as far as the numbers go, meaning like of the 14, about 4 or 5 are conceptual, or it could just be points wise, it splits that way. So it may be about 33-ish points, 30 to 35 really, for conceptual questions versus the remainder is calculation based points. The next thing is just going to be recapping each chapter and saying, all right, here's some of the more important stuff from each. I'll go through this quickly. If there are any questions or clarifications that you have, please feel free to jump in, ask me about any of it. This is just like a real fast jump in, tell you this is the kind of stuff we'll be doing during the exam, but I'm happy to go into more detail than that if needed. So chapter 1, it's really not a super important chapter for the exam. There are unit conversions, and that has been important for other chapters and homeworks and stuff like that, but I don't emphasize unit conversions on exams. Meaning, unless I screw up, you don't have to do any conversions on exams beyond maybe like hours to seconds, something like that. There's not any serious conversions. And sig figs was never a thing for us. We just had to mention it. But trig, of course, it shows up over and over and over through the rest of the chapters. So that's the sense in which the stuff from chapter 1 is important, because it shows up again in later chapters. So all the trig stuff you definitely need to be comfortable with. You can expect me to use like the north of west, north of east, that kind of stuff, phrasing for directions, and I may ask you to specify an angle as north of east, south of east, or whatever else. And then calculus will say where that comes in when we look at that in the next chapter, which I don't know where stuff went for the chapter 2 part of this, but anyway. In chapter 2, the main, most important thing is, of course, the kinematic equations, because that's sort of what the whole chapter leads up to. So I'll jump ahead to those for a moment. One of the big points things for this chapter, calculation-wise, is can you apply the kinematics equations to a given situation? So questions like these, or like what's in the homework or practice packets, are to be expected. I usually don't give a picture for the exam questions. You'll need to draw one to help you sort of understand what the problem's asking. The main mistakes I usually see on kinematics problems are your signs, SIGN signs, because if I tell you, for instance, something slowing down, you have to remember that that means velocity and acceleration are in opposite directions. I can phrase the question so that that's not obvious. For instance, I could say something is slowing to a stop. Its velocity is due east. Tell me about the time it takes for it to come to a stop. And you would just have to know that that means the acceleration is going to be negative because the velocity was positive. Same goes for free fall. The thing that people mess up on free fall is just this. Just not wanting that to be true. The acceleration is always 9.8 meters per second downward in free fall. No matter how I try and twist the question so that it doesn't seem like that's true, it's true in free fall. If we're dealing with horizontal motion, the acceleration can kind of be whatever, right? You can set your acceleration in your car, but for something that's just under the influence of gravity, it is always 9.8 downward. There will be probably one or two questions about position time graphs. For that, just remember that velocity is the slope of the position time graph. So for us, that usually does mean like straight line slopes. I'm not expecting you to do a lot of calculations of derivatives for graphs. It's just remembering that velocity is slope on these graphs, and then being able to interpret other things about them, like is it speeding up, slowing down, changing direction, and you can tell that kind of stuff also by what the slope is doing. There could be one, like flat out, I give you an equation for the position of something, like the position is given by blah blah t cubed plus something t squared and so on, and I ask like when does it come to a stop? For that you'd find the derivative, because that will give you the velocity. You see when that derivative is equal to 0, because that will say when does the velocity equal 0, when does it stop, and then you would find time. Questions like that, there might be one of, just to say, we do use calculus sometimes in here. That's chapter 2. There won't be a graphical integration problem on there, so you don't have to worry about this stuff for the exam. All right, vectors. You can also more expect vectors to show up in the context of other questions, not usually on their own. For instance, those questions where I give you a set of directions and I ask for the total displacement of the object. So they go east, and then they go north, and then south of east. What is their overall displacement as a magnitude and direction? You need all the tools that are developed in this chapter to be able to do that. So I will say that every bit of the chapter is important, but in the context of questions like this one. You can definitely expect a question very similar to this one to show up, and it would be a pretty hefty point value one, like 15-ish points, because there's just so many steps to it. It's so many points to award or things that can kind of go wrong. This last page of chapter 3 is your summary of the entire chapter and how you add any set of vectors. So if you understand this chapter, if you understand this page, you understand the chapter. Chapter 4 is generalizing the 1D stuff from chapter 2 to 2 dimensions or 3 dimensions. Let's see, the main stuff from this chapter will be the projectile motion stuff. For projectile motion, the main things that people, again, forget about are still acceleration, but really more so what that says about the velocity. The fact that the acceleration is 0 horizontally says your horizontal velocity never changes, is always the same number, and that gets forgotten in several different ways. The main one is, if you got something at the peak of its arc or parabola, it's tempting to say that it stops there, because that is true in free fall motion where it's going straight up and down. But that's because the vertical velocity is 0 up there, not the entire velocity. It still has whatever horizontal velocity it started with. The vertical is the one that changes the same way it does in free fall. And that's all sort of summarized conceptually here. And then the math is, it's kinematics twice. The main thing to be careful of for the math is that you make sure you're dealing with your components. You find those first, rather than throwing this into your table. You need to find the components of your velocity before you can do anything with them. Now there are cases, and there's several of these in the practice packet, where you'll see that something is launched horizontally. So, something like that. In that case, what is the initial vertical velocity?
Would it be 0?
Yes, it is not moving vertically at all at the beginning. It is going to start picking up some vertical velocity as it falls, but initially 0, meaning whatever velocity they tell you it's launched at is secretly actually your x component, because that's all there is initially. So if they tell you something's launched horizontally at 50 meters per second, that's secretly telling you the horizontal component is 50. If something's launched at an angle, then you do need to separately worry about like how much of that is x and how much of that is y. But if they say launched horizontally, you're being told 0y and then some whatever the value that's given for x. And that's really it. There could be, like I said, like just straight taking derivatives like this, but that usually goes fine. It's really just the kinematic stuff that there's a lot of trouble with, and so that would be a big one to practice on, make sure that kinematics is comfortable. What questions do we have?
So you said that we won't have to graph. Is that what you said?
Um,
You said something about graphing. I just forgot about it.
so for graphs, I think I was saying like there will be these position time graphs. You'll still have to like potentially tell me what the velocity of something is or its acceleration or something like that. But primarily for
Mm-hmm.
graphs that look like this, like it's all straight line segments, not the ones like this where you've got curves.
Mm-hmm.
That's really it. That for graphs, you'll just have straight line graphs.
And I believe in the beginning you had told us the breakdown of the exam. Could you repeat what you'd said again?
Yeah. So it will probably be 10 to 14 questions. About 1/3 will be conceptual and 2/3 calculation.
Okay, thank you.
Hmm. Other questions?
I have a question about the kinematics equation. So, depending on the table that we use, I think the only trouble that I'm having is like figuring out which equation to use,
Hmm.
like based off of the table. Like, do we have to find the equation based off of what's missing in the table?
It's sort of like you're hunting in the question statement for three things that are given and then one thing that you're being asked for. And then you look for the kinematic equation that relates those things. So if I come back to the list, if I'm trying to find a certain kinematic variable, like they're asking me how long something takes, the time, I'm not looking for the one where it doesn't show up. That's not what that means. I'm looking for one where it is part of the equation. So one of these four might be my potential kinematic equation to use, depending on the other three things I'm given. If the other three are acceleration, initial velocity, and final velocity, I want to use this first equation. If the other three things that are given are these things, I want to use that one, and so on and so forth. So it's just based on what you are asked to find and the other three things that you're given.
Okay, thank you.
Uh-huh.
So is it going to be 10 to 14 questions per chapter or just total?
Total.
Okay.
Yep.
And we are allowed to bring a cheat sheet, or
Yes.
how would you want us? Okay.
It can, like, it's pretty hard to do it wrong as long as you have just done one side of a sheet of paper. Um, if I see stuff on the back side of the paper, I do dot points sometimes if it's clear that it wouldn't have fit on the front side. So one side only, but it can be typed, it can be handwritten, you can cut out pictures and tape them on there. I've seen that before. However you want to do your cheat sheet is fine with me, and whatever you want to put on it is fine with me.
Okay, thank you.
Mm-hmm. Are there specific problems we want to look at or anything like that?
Um, the one in chapter 3 where you'll have something moving in like 3 directions,
Okay.
like to go for overall displacement.
So let's come over to practice exam and I'll find a similar one and we'll just walk through it. Let's just do this one just because it's got the most complicated directions to it. All right. So this is a really boiled down version of what all the other questions like this are asking. It's just asking you to do vector addition with these three vectors. So let's say we've got north, south, west, east. And we just imagine walking along the steps that they're giving. So vector A is to the east for 56 kilometers. Vector B is 11 kilometers at 22 degrees south of east. So I look in the second direction, turn towards the first. I look to the east, turn south of it. So they're saying I walk something like that, where this is 22 degrees because I'm turning that much south of east. And so this is 11 kilometers. And finally, 88 kilometers at 44 degrees west of south. So I look towards the south and turn 44 degrees west of it. Well, if I'm standing right here and I'm looking south, turning 44 degrees west of it would mean I'm now looking something like this way. And they say 88 kilometers, so it's a pretty large displacement, maybe something like that. And if they're asking me to do vector addition, they're really asking me, what is my overall displacement? What is the shortcut? All right, now that I've drawn my picture, that's the hardest part. If you get the picture right, the rest follows. So let's see, let's make our table. So we got our three vectors, and then we want to add them to find our overall displacement vector. So help me out with the components of these vectors. Tell me for vector A.
Okay, I was gonna just say I know the x component
Oh.
is positive.
Uh-huh. What about the Y?
Would it be 0?
Yep, because they're going due east. There is no north or south component to that. So 56 kilometers. All right, someone else, tell me for vector B about its components.
For X, would it be negative? And then for Y, be negative as well. And I think it's for X, 11 cosine
Okay.
22 degrees.
Yes, it wouldn't be negative though, because let's sketch in for vector B.
Oh, wait, a positive. My bad.
Oh, you're good. So yeah, it is a positive 11, and then it's kilometers, cosine of 22.
I was gonna say Y was negative
Mhm.
11 sine 22.
Yep. All right, and that's because if we go to our picture over here, for vector B, you have to walk to the east and south, so to the right and down. The x component of that is adjacent to the 22-degree angle, so that's why we use cosine for it. It's to the right, so it's positive, and then it's just whatever the magnitude, the length of the original vector is. And then for this one, it's downward, and it's across or opposite from the 22-degree angle, so we use sine. All right, someone else for vector C, tell me about its components.
X is negative and Y is also negative.
Yep, because we have to walk down and to the left for vector C. All right, tell me about which one I should use sine for and which I should use cosine for.
Would you use sine for the x component and then cosine for the y component?
Yep. So if I sketch those in, I walk down and I walk to the left. So I see that the x component is all the way across from the 44-degree angle. It's opposite it, so I use sine. It's to the left, which is where the negative comes from, and then it's whatever the magnitude of that vector is. So negative 88 sine 44. And then what about the y component? So it's negative,
Negative 80 cosine 44.
yep, because it's adjacent to that 44-degree angle. I will just remind us, like, I could have drawn my components this way, to the left and down, instead of down and to the left. It's still correct to do it that way. I just didn't because it doesn't, this right triangle I've drawn doesn't include that 44-degree angle. So I'd have to do some more work to do trig with those two sides. So this is 88 kilometers cosine 44. And from here, it's just going to be some calculator work. I have to add down the x column to get the overall x component. That'll be some number delta x. Do the same for the y. That'll be some other number delta y. And if I want to write out the resultant, I have two options. On the exam, I would ask you like to use find a magnitude and angle if that's what I want, or the components if I want that way. But that would be for components, or rectangular form of a vector, same thing. You'd write it like that. If you want the polar form or magnitude and angle, it's Pythagorean theorem. And your angle is inverse tangent, usually y over x, because in this case, you're the one picking how you specify it, and usually you would specify relative to like due east instead of due south. The absolute values are so your calculator doesn't spit out something weird, and then you'll just know that if it says an angle of like 70 degrees or whatever, it means this angle is 70 degrees, something south of east, for instance. So we could put in those numbers, but that kind of finishes out the problem.
So, you would like specifically ask for the magnitude of that vector or the angle or
Yeah,
whatever else?
yeah, I would say something like find the magnitude and angle of the total displacement of whatever the thing is that's moving, and express the angle as like south of east or relative to due east, something like that.
Oh, so you would give us the direction to use
I would
or like
I would at
the base
least
off of?
yeah, I would at least say something like relative to due east, so you would know that you have to say either north of east or south of east by some angle. And even if that goes wrong, I grade heavily on partial credit. It's not like if the final answer is wrong, it's wrong. Getting the correct final answer is usually worth about 1 point out of 8 or 10, however many it is for the problem.
I have a question.
Yep.
So the recent homework of chapter 3,
Mhm.
question 11, will we have something like that on the exam, or is that something I don't need to worry about?
Could you describe it?
Okay. So we were given like two vectors, and we had to find the magnitude, the angle counterclockwise from the axis defined by the I guess I hat, and magnitude and the angle again, and then we had to find like the angle of
Oh,
the
yes.
vector a plus b.
Well, for that one, it had, if I remember right, it's like find, yeah, the components of A, components of B, components of A plus B, magnitude and angle, components of A minus B, magnitude and angle. So yes, in the sense that that's kind of what you're doing with any problem like this. No, in the sense that I'm not going to ask you something with 11 parts to it.
Oh, that picture you were just drawing,
Mhm.
that looked like one of the homework problems. Could you, I mean, is it more of the same of what we just did right
It
here?
is, yeah. So it's the exact same stuff. The only thing that makes it seem so much harder on Wiley is that they want the angles specified in the way you're used to from like a math class, like trigonometry, which makes it really inconvenient. So, for instance, I think in this problem, you had to find the overall displacement, which would be that vector, and then they ask for the angle, but they want it relative to the positive x-axis. So they want that angle, when really what the inverse tangent thing is telling you is just this angle. So you'd have to add 180. I don't do that on exams. I really am just asking for like the most obvious angle. I just can't turn it off in Wiley, and I hate it too. So with that, I try to provide some hints. But yeah, there's still some kinks there of like they want negative angles or just all crazy sorts of things.
So you won't have like problems where you'll ask us to basically do 180 minus whatever to get like the angle relative to the x-axis, positive x-axis.
Right, yeah. So I like, for instance, here you could also have answered this one by saying, okay, subtract this angle. Actually, let me delete some stuff to clear that up. So if they wanted relative to the positive x-axis as a negative angle, they'd want this angle. And how you would do that is find this one and subtract that from 180 and call it a negative angle. I still think that's just too much. Like, I really just want this angle. And you would say it is south of west.
Okay.
Yep.
And you'll let us know when you want us to have like the direction, like would the south of west or the north of east, would that go underneath direction?
Yeah, so you would say like,
Okay.
for instance, if this one were like 50 degrees, you'd say 50 degrees south of west.
That's how you'd like us to answer all the questions?
If they're asking for an angle like that, yes. But the other thing is, all right, say this is the final answer for the degrees, right? The overall question might have been 14, 15 points. This is half a point. This is half a point. What really matters is you finding the components, all the work that led up to that, all this stuff. That's where the points come from. So even if the final answer is a little bit quirky, because Wiley has messed you up so much with how weird it wants angles, it's okay. It's not a big impact.
So mainly just showing your work is where most of the points come from, depending on the question, right?
Absolutely. Yes, that is something it should be stressed. It might seem obvious, but sometimes people will get into a problem and then get confused and then erase all of their work and then just write some random numbers down and move on. That's how you get 2 out of 10. If you want 8 out of 10, leave your work there. It's probably pretty close to the right answer and you weren't able to finish it out. That's a lot better. The only ones where it is like all or none is when you see a multiple choice question, because then it's like you can't be half right if you circled B, but the answer was D, you know? You gotta pick one. And those are pretty clearly laid out. They're called no work required or NWR questions. Those are the only ones where there isn't partial credit.
Speaking of that multiple choice question you were just looking at, will we have anything like that?
On an exam, no, because this is essentially asking like add the vectors. So it is like this question. That kind of thing would already show up in a calculation question like this. So this is just to kind of practice that skill of knowing what vector addition means, what it looks like.
Okay, and I have just like one more like kind of general question. So if a vector in your drawing or in your graph or whatever,
Mhm.
if it's just going straight like horizontally or straight vertically, either the x or y component of that vector will be like 0
Yes,
because it's not at an angle.
absolutely. Yep. And so to come back to that, just to give one more reason why. So let's say this is your vector. In the like trig class version of this, it would be that we always use cosine for x and sine for y. I still stick with cosine is adjacent, sine is opposite. But let's say we're measuring things relative to the x-axis here, and I want to find the x and y components of that vector A. I could, if I didn't just say, oh, it's all A in the x and none of it in the y, I could be a little bit more extra about it and say, well, that vector makes an angle of 0 degrees with the x-axis. So my x component is A cosine 0, and my y component is A sine 0. I don't have to just throw out cosine and sine, but it really doesn't matter because cosine of 0 is 1, sine of 0 is 0. So I get that my component is A, and then 0 for the y component. Anyway, I just skipped that step because it's kind of obvious from the picture that that's what my components will be. Does that make sense?
Yeah, it makes sense. I think I was just like thinking about it too hard.
All right, other questions?
I have another question regarding the exam. Is it just to clarify, like once we get our score back and the questions that we missed, can we like go back to do like test corrections?
You do get test corrections for one exam over the course of the semester. And so how that works is once you get your grade back, you get like a week to kind of decide if you want to use your test corrections for that exam. And then you will basically re-attempt the question. So write down your new attempt either on the exam or on a separate sheet of paper, doesn't matter. And then you turn that in and I regrade it and I give up to half points back. So if you originally got a 50 on the exam, that's 50 points you could have earned that you didn't. Half of that is 25. So you can get 25 points back on your exam if you get everything right the second time around. When I say I only let you do that on one exam, that does mean like if you choose to do it for exam 1, you can't for exam 2 or exam 3, and you won't know what they look like until later down the road. I know that's unfortunate, but the alternative is I have to regrade everyone's exams at the end of the semester, right after exam 3 and right before the final. It's not feasible or humane to me, to be honest. And I will kind of go back over all that once you get exams back.
Can you go over a kinematic equation problem?
Sure. In 1D or 2D?
2D.
Okay. Let's see. All right, let's do one where it is launched horizontally, and then we'll do a different one where it was launched at an angle. So a ball is thrown horizontally. Again, that's automatically telling me my initial y velocity is 0. And so whatever the initial velocity is all x. They don't actually tell me what it is in this problem, though. It's from the top of a 20-meter high hill. That's telling me something about the height, the y. It hits the ground at an angle of 45 degrees. That's theta. What speed was it thrown with? All right, so it's asking what is v0? But since it didn't have any y velocity initially, that's really asking what is v0x, because that is the entire velocity. If it's thrown horizontally, it has no y velocity. All right, so I'll make my two tables. And so we know the initial y is 0. We want to know the initial x. We know that for something, a projectile motion, it's 0 horizontal acceleration and negative 9.8 for the vertical. And the last thing we know is this y right here. But we have to be careful because the object falls by 20 meters, meaning its vertical displacement is actually negative 20. It goes down by 20 meters. From that, it looks like we're actually doing okay filling in the y part of these tables. For the x, which is ultimately what we're going to need, not so much. So at that stage, I might say, how about I find the time? Because then, I'm not saying it's 0, I'm like circling. How about I find this thing right here? Because that's going to be the same for the x motion and the y motion, and that'll give me one more thing for the x motion. So let me start by doing that.
Sorry, why did you do negative 20 again for the y? I see that I see the 20 meters, but why did you make it negative?
Yeah, so we have to remember that y is really representing the vertical displacement of the object. And if it started up here at the top and ended up down here, its displacement is downward. It went downward overall. That is a negative displacement. Does that?
Okay, thank you.
Uh-huh.
Yeah, it helped.
I have a question.
Yeah.
Why again is the horizontal acceleration 0? I know we covered it in class, but I forgot like conceptually why it is that way.
Because gravity is the only force acting on the object while it's in the air, and gravity only pulls downward. So that kind of stems more from the chapter 5 stuff now that we've seen it a little bit more. The only way you're going to get an x acceleration is if there's a force acting in the x direction. And there isn't here. It's just gravity pulling downward. Does that make sense?
Yeah, it makes sense.
Okay. All right, so now we are down to, I'm going to find the time here. So time is 2y over ay, take a square root. And let me calculate that. About 2.02 seconds. All right, let's see if that's actually going to help me for my x stuff. Because now I've got sort of 2 things I know and 1 that I don't. I do also know that Vx and V0x are going to be the same number because horizontal velocity, it's constant. But it's still sort of like I've got too many unknowns. So let me start thinking about this angle of theta. All right, it's maybe like I've hit a dead end here, and I want to try and approach it a different way. They tell me it hits at an angle of 45 degrees. So it'll have a certain Vx and a certain Vy to it. And this is 45 degrees. I know that tangent of 45 degrees is Vy over Vx, at least up to, right, this absolute value thing. What is tangent of 45 degrees?
Is it 1?
Yeah, it's just 1. What that's really saying is that these components, Vx and Vy, are the same size as each other. If something's hitting the ground at exactly 45 degrees, it's got just as much x velocity as y velocity, right? Because I could rearrange this to say the size of Vx is the same as the size of Vy. The absolute value is just to say, numbers-wise, it's the same number, although in this picture we can see Vy is actually negative and Vx is positive. So I might take this and run with it, because it tells me if I find Vy, that'll tell me Vx automatically. They've got to be the same number, just up to a sign, a plus or minus. So all this stuff I just did, it's probably how you would approach the problem from a first pass, but it's actually, it could be maybe not what we need. So let's sort of make a break here. In the practice packet, like the solutions, I kind of gave the direct solution, but this is how you might approach it on an exam. So I'm gonna see if I can find Vy. That's my new task here. But I can still use the same sort of information I already had. It's just I might use a different kinematic equation now. One that relates the 3 things I have, these 3, but now to Vy instead of to the time. So Vy is square root the initial y squared plus 2ay. Oh, I'm missing a little subscript. And that's going to be the initial y is still 0, so I'm really just calculating square root of 2a and then y. And this is where that negative in the negative 20 becomes important, because otherwise you'd be taking a square root of a negative number and get very concerned about why that's happening. So what we get here is about 20 meters per second. But I do also have to remember this is a plus or minus sort of deal, right? When I take a square root, there's 2 roots. I'm going to take the minus root because Vy is downward. Remember my picture up here. Okay. We're almost done. We're in the home stretch. What I've done is I've found my final y velocity. From this stuff up here, I know that must be the same as my final x velocity, at least up to a sign. So my final x velocity is also 20 meters per second. For my picture, I can see it's positive 20 meters per second. Last, I know that my final x velocity is the same as the initial, because it never changes. So my initial x velocity is 20 meters per second, and that is the overall initial speed it was thrown with, because the ball was thrown horizontally. That is a hard question, like on the upper end of just difficulty for these types of questions. But do y'all see the chain of reasoning?
Yeah, I see it. For a question like this, how many points would you probably give on the exam for this?
Something like this would be 10 to 12. I would say I probably would go something a little bit easier. So let me hit one that's maybe more akin to what you could feasibly see. I just wanted to show this one because it's really like worst case scenario. So let me do one that's a little bit less worst case scenario. I should have picked better at the beginning. We've got a boy on the edge of a vertical cliff 20 meters high, so I would start sketching. He throws a stone horizontally outward with a speed of 20 meters per second. The fact that it's horizontal still tells me it had no initial vertical velocity, and this is my initial horizontal velocity. How far from the foot of the cliff does the stone strike the ground? And this was 20 meters. So I want to know this x value, horizontal distance. So I'll make my 2 tables. I want to know this. I know this is 20 meters per second. Since Vx is always the same as V initial x, I could put it there too. Ax is 0. And then for the y, the stone again fell 20 meters. So I know it's negative 20 meters for the displacement. It has 0 initial y velocity. Ay is still always negative 9.8. And so we look at this and again say, all right, what are my options? So it kind of looks like I've got 3 and can find a 4th here. Let's look at my kinematic equations that could be relevant. So let's come all the way up here. All right, so I'm looking at this line. I might say, oh, I could use this one. It doesn't give me x, so maybe it's not a great candidate, but there's another reason it's not going to be super helpful. Since ax is 0 for projectile motion, this equation's really just telling me final equals initial. I already knew that. So I might move to this one and say, okay, maybe I could use this, but I need to know the time. So still not quite there. I look at this one. I say, all right, again, could maybe use it, but need to know the time. And then last I come to this one and say, oh, this looks promising. It's got x, it's got vx, it's got v initial x, it's got ax. But again, ax is 0. So when I put this in, I'm not getting anything useful out of it because I'm multiplying the thing I want by 0. If I try and bring ax over to the other side, I again have problems because I'm dividing by 0. You can sort of run into this sometimes, and what it makes you realize is there's not really a good option unless you find the time. So we need to do that first. But that's okay, because I've got my y motion stuff. That's going to let me find the time pretty easily. The equation that'll be best for that is probably this one. And you can see this is sort of reading similar to our first attempt of this problem. My initial y velocity is 0. And so I solve this for time. It's 2y over ay. Take a square root. Ay was negative 9.8. And I'm just going to cheat off myself here. I had already found that because the numbers happen to be the same in this problem. It's about 2.02 seconds. All right, so I know how long it takes to hit. But now I can put that information up here, and I can use it to find the distance. I could use any of those equations that looked promising before. I might pick this one, and then just recognize that since the acceleration is 0, this is really just telling me that distance is speed multiplied by time. So 20 meters per second times 2.02 seconds, it's going to hit around 40 meters away from the base of the cliff. And that's my final answer. That's more like what you could expect on the exam. And then I did say I was going to do a one with it launched at an angle, so let me just do this first question for that to see what the difference is. It's a slight difference. So we've got a cannonball aimed 30 degrees above the horizontal, launched with an initial speed of 125 meters per second. Question is how long it takes for the cannonball to hit the ground. Well, it's going to go in an arc and eventually hit somewhere over here. It's asking me how long that takes. So, make my tables. And if you have a different way that you like to do this, like you've been following someone else online, like Organic Chemistry Tutor or whoever, use a different notation, do whatever works. I'm not a stickler for it's got to be my way or nothing. As long as it is a consistent way that's like not just you kind of jumbled the numbers together and saw what it spat out. As long as it is a correct way to approach the problem, I'll figure it out. All right, so what do we know here? I have that 125. What I need to be careful about is that's not my initial x or y. So I need to find those. This is v0x. This is v0y. So I can see that v0x is going to be positive, v0, and it's adjacent to the 30-degree angle. So cosine 30. v0y is positive, v0, and it's opposite the angle, so sine 30. And so if I calculate those with v0 being 125, this is 108 meters per second, and this is 62.5, that's so positive, meters per second. So I can put that in here. And use my sort of free spaces, my accelerations I always know. And I want to find time. So that could still possibly be from either set of axes. But then the last observation is the cannonball's hitting the ground at the same height it was launched from. So my vertical displacement is 0. It ends up at the same height it started at. So between the x and y motions, the y is probably going to be the more helpful here. And so I pick a kinematic equation that relates those 4 things. You may be noticing we use this one a whole heck of a lot in projectile motion. It's usually a safe choice as a first pass. It may not be the one you need every time, but it's not the worst choice you could make. All right, so I need to know the time it takes, and there is the painful way to do this or the shortcut way. The painful way is I'm solving this equation for time. It's a quadratic equation. I need the quadratic formula. The shortcut way is to recognize for this problem that the vertical displacement is 0. So I'm really solving this problem. I can factor out time. If the left-hand side of this is 0, either this has got to be 0 or this whole thing has got to be 0. So that means either time is 0 or the stuff in parentheses is 0. I don't want this solution because that's when I first launched the cannonball. That is a time when it's at 0 meters off the ground, but it's the start of the problem. This is the one where it lands, where it hits the ground again. So I'll solve that. The initial y we said was 62.5. And then over 9.8. And if I calculate that, I get about 12.8-ish seconds. All right, so if something's launched at an angle, really the main thing that gets worse is you have to find the components of that initial velocity and then proceed as usual.
I have a question. So with these kinds of problems, like you said before, we're using that particular kinematics equation. So you're saying that we can use it like as a safe way to do it? Is that what you're saying?
I'd say, so there's always going to be, depending on what problem you're doing, like the most direct kinematic equation that'll get you to the final answer. I'm just saying if you have no idea which kinematic equation you should use, you could try this one first. It's not always going to be that one that's going to get you to the right answer immediately, but there are worse ones to choose as a wild guess, if that makes sense.
Okay.
Yeah.
Thank you.
If it doesn't work, you may need to choose a different one, and that's still just the same way you choose any of them. You look at what you've got and then what you want to find and pick the one that relates those 4 things, but it tends to be this one a lot of the time for projectile motion stuff.
I have a question about the free body diagrams.
Uh-huh.
So if I put the angle like in reference to the x-axis, does that allow me to keep it like in cosine and sine, or?
Yes. So that goes for, so technically free body diagrams is for forces, but if you just mean like this stuff up here, still the answer is yes. If you're always measuring relative to the x-axis, then you can say that the x component is always cosine and the y component is always sine. I just like the freedom of knowing if I just say use cosine for adjacent and sine for opposite, I can use whatever angle I want. But if you like sticking to the x-axis, you can do that. You just got to make sure you're always converting your angles to something that is measured relative to the x-axis. So maybe just as an example of that, from this problem, we used this 44-degree angle. If you really like the x-axis, you might instead use this angle, which is, let's see, 46 degrees, because they have to add up to 90. In that case, the x component of vector c, you would use cosine, the y component you would use sine. If you want to be even more of a stickler of like, I always want to use the positive x-axis, in that case, you have to measure that not as 46 degrees, but 180 plus 46, so 226 degrees. In that case, you don't even have to do the signs out front of these things. They will fall out automatically by using that 226-degree angle. But that is such a weird way to look at that angle to me that I never do it that way. So what I mean is, instead of putting negative all this, if you wanted to do it with that 226-degree angle, you would write it as 88 cosine 226 and 88 sine 226. And the negatives would fall right out of that for you. You wouldn't need to separately put them. That seems nice, but again, you have to recognize this is your angle, and I can't even see what right triangle that corresponds to. So it's just a strange way, personally. If you like that better, go for it. All right. If there aren't, that's fine. You're still free to email me with any questions you have and ask in person once we are back in person. So y'all enjoy your day, enjoy your weekend, and let me know if you do have any questions pop up.